Hello friends, here we are going to solve a question from Indian Regional Mathematics Olympiad or RMO of 1993. And here is the question. We have to show that the tens digit of any power of 3 is even. That means the second digit from the right for any power of 3 is even. Now to elaborate that, I have actually already written a few initial powers of 3's here. The first power of 3 is 3, which I have written as 03. The second power of 3 is 9, which I have written as 09. Then you can see the rest of the numbers 27, 81, 243, 729, etc. Now in each of these cases you can see that the second digit from the right is an even digit. In fact, for the first two powers of 3's, since the results are single digit numbers 3 and 9, I had to add a leading 0. Now adding a 0 in front of a number does not change the value of that number, so you can basically assume 3 to be 03 and 9 to be 09, and 0 is a even digit, so we don't have a problem for 3 and 9. And even for the rest of the numbers, for each of the numbers you see the second digit from the right, that is the tens digit, is always an even digit. For 27 you have 2, for 81 you have 8, for 243 you have 4, and all this. Okay. Now it seems that this claim is true for each of the powers of 3, but we have to logically prove it. So how can we proceed? Well, before we try to prove this for the powers of 3's, let us first try to understand, let us first try to find a common property of all such positive integers, not necessarily only the powers of 3's, but all such positive integers which will have an even digit at the tens digits place. Well, we can easily observe that any such positive integer that has an even digit as the second digit from right or as the tens digit can be written as a number which is a multiple of 20 plus some single digit. Let me explain that by an example. Let's take a random such positive integer which has an even digit as the second digit from right. Let's take some number like 149. Let's take 149. Now 149 is a positive integer that has an even digit as the second digit from right, or as the tens digit. Now 149 can be written as 20 into 7 plus 9. So it's basically a multiple of 7 plus some single digit. You can take another example like let's say 243. It can be written as 20 into 12 plus 3. Again you see 243 is basically a multiple of 20 plus a single digit. In fact, in mathematical notations we can write that any positive integer n which has an even digit at the place of tens digit will be congruent to a single digit mod 20. Now what does this mean? It means that the number n when divided by 20 leaves this delta, which is a single digit, as the remainder. This delta is a single digit which can be either 0, 1, 2, 4, 5, 6, anything up to 9. It's just a single digit. Or in other words, if you subtract this delta from n, then the result will be perfectly divisible by 20. This is the meaning of this line. And any such positive integer that has an even digit at the tens digits place will have this property. Now let us come back to these powers of 3's. For the first two powers of 3's, we have settled the case. We have assumed 3 to be 03 and 9 to be 09, and 0 is an even digit, so we are good there. What about the remaining powers of 3's? The first multi-digit power of 3 is 27, and the subsequent powers you get by repeatedly multiplying any power of 3 by 3. So when you multiply 27 by 3, you get the next power, which is 81. Then you multiply 81 by 3, you get the next power, which is 243, and you keep on doing that. So the first multi-digit power of 3 is 27, and 27 is congruent to 7 mod 20. That means 27 when divided by 20 leaves 7 as the remainder. Okay, fine. Now to get the next power of 3, what do? You multiply it by 3. And when you multiply this number by 3, you get a result. We know that when you multiply it by 3, you get 81. But in general, if you have a number that is congruent to 7 mod 20, and when you multiply that number by 3, you get a result which is 21 mod 20, because 3 into 7 is 21. But 21 mod 20 is kind of absurd, because the remainder always has to be lesser than the divisor. So 21 mod 20 can be actually written as 1 mod 20, because 21 is nothing but 20 plus 1. That means if you have a positive integer which is congruent to 7 mod 20, and then if you multiply that integer by 3, you get a result which would be congruent to 1 mod 20. Again, if you multiply this number by 3, you get a result which will be 3 mod 20. You further multiply it by 3, you get a result which is 9 mod 20. And if you further multiply it by 3 again, you get a result which is 27 mod 20, because 3 into 9 is 27. But again, 27 mod 20 is absurd, because this number has to be this number has to be lesser than 20, and this 27 mod 20 can be rewritten as 7 mod 20. Now 7 mod 20 is exactly what we have started with. So we are back to the very first step of the iteration. Again, if you keep on multiplying this by 3 and the result again by 3, if you just keep on doing this, you will be basically iterating in this loop. So first number would be 7 mod 20, then you would get some number which would be congruent to 1 mod 20, then you would get some number which would be congruent to 3 mod 20, the next number would be some number which would be congruent to 9 mod 20, and again you are back to some number which is congruent to 7 mod 20. So basically you will be forever iterating in this loop. And since each of these numbers is of the format congruent to some single digit mod 20, be it 7 mod 20 or 1 mod 20 or 3 mod 20 or 9 mod 20, is always some single digit mod 20. That single digit is either 7, 1, 3 or 9. But since each of these numbers is congruent to some single digit mod 20, that means each of these numbers will have an even digit at the tens digits place, or the second digit from right will be an even digit. And we have started from 27, and we got this cycle by repeatedly multiplying these numbers by 3 again and again. So it proves that any subsequent powers of 3 starting from 27 will have the second digit from right, or the tens digit, as an even digit. So here we have proved the claim made in the question, friends. I hope you have enjoyed this video. So feel free to like, share, comment and subscribe to my channel. Thank you.